Hello everyone, this is Jiliang Wang from Tsinghua University. The paper I'm going to present today is BlueDoor, breaking the secure information flow via BLE vulnerability. This is a joint work with my students Hu Feng and Zhou Ye from Tsinghua University, and my colleagues Han Yi, Zhe, and Yunhao Liu. We all know that Bluetooth Low Energy has been widely used in the IoT era as one of the most important communication protocols. It can be used for information exchange between two devices. It also extends the network to more and more peripheral devices, so its security is of great importance in today's network. In this paper, we investigate, is BLE secure enough in practical applications in IoTs? This figure shows the basic workflow of BLE. To set up a connection, a peripheral device first needs to advertise packets, including its basic information. Upon receiving the advertising packets, a central device such as a mobile phone can establish a connection with this peripheral device by sending connection request. After that, those two devices can negotiate on whether or not to use encryption in the connection. And then the central device can send authentication information to the peripheral device. After that, those two devices can exchange information using BLE connection, and the central device can read and write all the characteristics in the peripheral device. The data in BLE are stored in the form of characteristic, which includes the following fields: the UUID field, which is the unique identifier; the handle field, which is the access address of this characteristic; the property field, which specifies the permitted operations, including read and write; the secure field, which is the access control, including no security, encryption required, authentication required, encryption and authentication required. For example, encryption required means that this characteristic can only be accessed by a connection with encryption. Finally, the data are stored in the value field. Basically, based on the mechanism of using encryption and authentication, the BLE link can be very secure in theory. For example, the attack cannot decrypt the data packets in the link as it cannot get the encryption key. Meanwhile, the attack can also cannot set up a new encryption key with the peripheral device, since this usually involves user participation. However, in our work, we show that we can pass the encryption and authentication in practical BLE applications. As a result, we can read and write all the characteristics in BLE link. This also implies that the widely used BLE may not be secure enough in many application scenarios. We assume that they are pre-built encryption keys and authentication certifications between two devices, and the attacker cannot physically touch these two devices. Meanwhile, the attacker can send and receive packets on a specific BLE channel. The main workflow for our method BlueDoor is shown as follows. First, as those two devices have built a connection before, so the first step for the attack is to interrupt the connection using a signal jammer. After that, the attacker can establish a connection with their peripheral device using its advertising packet. So after this step, the attacker can already access the characteristics of no security. However, it cannot access those characteristics requiring authentication or encryption. So the first key problem is how to deal with the encryption, or more specifically, how to obtain the encryption key. In our method, instead of obtaining the old encryption key, we set up a new one. We show that the attack can generate a new encryption key without user participation. We propose the silent pairing method, which can build a new encryption key without user participation. There are 4 levels of pairing in BLE. The first one is just works, in which 2 devices can negotiate the encryption key by exchanging wireless packets without user participation. The second one is numeric comparison, in which devices will generate a 6-digit code and the users need to confirm the code on the devices. The third one is passkey entry, in which one device will display a 6-digit code and users will enter this code into the other device. This is probably the most commonly used pairing method in practice. The fourth one is auto-band method, in which some auto-band channel is used for encryption key exchanging. From top to bottom, more user operations are involved and it is supposed to be more secure. One may ask why BLE needs to keep those less secure pairing methods such as JustWorks. It should be noted that BLE needs to adapt to diverse devices, and in practice, many BLE devices have limited capabilities, so BLE needs to be compatible with those devices. We leverage this property in BLE. We found that 2 devices need to negotiate the pairing method according to their input and output capabilities. So the attack can force BLE to choose JustWorks pairing method by claiming to be a low capability device so that the attack can set up a new encryption key with the peripheral device without user participation. This also reflects a fundamental challenge in pairing for BLE. That is, BLE has no information about the connecting devices, and it has no other choice but to trust the device. After this step, the attack can access those characteristics in the peripheral device with the encryption requirement. The next question is how to bypass the authentication. First, you should be noted that the authentication information is saved on the central device, so the attack should leverage the central device. More specifically, the attack needs to pretend as the peripheral device to deceive the central device using identity spoofing. After that, the attack needs to obtain the plaintext authentication packet and use this authentication packet to bypass the authentication for the peripheral device. For identity spoofing, we know that in BLE, devices are discovered by their advertising packet, and also BLE identifies peripheral devices using MAC address in the advertising packet. So the attack can pretend as a legal peripheral device by changing its MAC address, and also it can connect to the peripheral device to suppress its advertising packet. This reflects a challenge in pairing devices in IoT. That is, device discovery and identification is not easy, not only in BLE. After that, the attacker needs to obtain the plaintext authentication information. Here, the attacker can just disable the encryption by rejecting the encryption request from the central device. This is mainly because that there is a negotiation between those 2 devices before using encryption. This is since devices have different types of characteristics in BLE, and different characteristics have different security levels. There is no need to encrypt all the characteristics. So in BLE, 2 devices will negotiate whether or not using encryption. This also reflects a key question in BLE design. That is how to trade off security and adaptation to diverse devices and data. After this step, the attacker can obtain the plaintext authentication packet and then forward the packet to bypass authentication. Combine those steps together, the attacker can access all the characteristics in the BLE link. We implement BlueDoor in the laptop with Bluetooth adapter. The software implementation is also based on several existing components we listed here. We evaluate the performance of BlueDoor in different central devices, including iOS-based smartphones and Android-based smartphones. We also evaluate the performance for different BLE devices, including fitness trackers, smartwatches, and so on. Unfortunately, for all those devices, we cannot find a characteristic requiring both encryption and authentication. So we emulate a device, Charlie, which can provide characteristics requiring both encryption and authentication in our evaluation. We show that BlueDoor can obtain sensitive personal data from a fitness tracker, but we can derive detailed user activities based on those personal data. This indicates a severe problem in privacy leakage. We further show that we can obtain secure SMS messages, as those messages are often delivered to peripheral devices in BLE as real-time notification packets. Unfortunately, those messages are often used for verification code delivery for a large portion of websites. Here we have a short demo. The laptop here is the attack, and it can conduct silent pairing and connection degradation in the BLE link. At this step, it can obtain the error messages when it is delivered to the peripheral device. Previously, this error message is considered very secure. Also, we can obtain the verification code in the SMS message. We can input this verification code to the website to change the password. Okay, that's all for the demo. We also conduct detailed evaluation for the BlueDoor. We show that BlueDoor can work on most BLE devices for silent pairing and connection degradation, except for on-band 3, in which we cannot get any response for connection degradation. So we cannot judge whether the connection degradation is successful or not. We show that BlueDoor can read all the readable characteristics in all these devices. To evaluate the performance of write, it is more difficult. First, we need to infer the format of write command. Otherwise, the write command cannot be successful. Then, checking the result of write command is also not easy, as not all the write requests will change the corresponding characteristics. So we use a conservative way by only considering the write command with responses from the device. We show that BlueDoor can write to all the writable characteristics except for 2 uncertain ones without response from the devices. To address these problems, on one hand, these particular problems can be easily addressed. For example, we can restrict the pairing method. The device should not always trust devices claiming with low capability, or we can enable both encryption and authentication in practice. However, we should emphasize here that there exists fundamental challenges and trade-off in BLE design and using BLE. First, discovering and identifying devices in IoT is not easy. Actually, not only in BLE. Meanwhile, a protocol is secure does not necessarily mean that the application is secure. For example, do not always trust. I'm secure since I used the secure protocol. Think about SMS message, which was previously thought as secure. Further, people need to pay more attention to security in IoT. This also raises another question. Should security be the first priority in BLE design or even in IoT design? Last but not least, do not blame BLE. That's actually not the fault of BLE. That's a challenge in IoT design. That's also a design dilemma that a protocol needs to adapt to diverse IoT devices. The protocol should be convenient and the protocol should be secure. So that's a big trade-off among those metrics. We also conduct a survey for different BLE users. For those 84 users, we found that 64% of people do not pay enough attention to the security of BLE data. The good thing is that 62% agreed to improve the security by sacrificing the convenience a little. For example, confirming the status of the connection each time the device reconnected. This should have some information for the device manufacturers and applications of BLE. So that's all for my presentation today. I'm glad to take any questions.